In this video, we follow up on our earlier discussion of aldehydes by exploring how to use the IUPAC system to name these molecules. This particular video focuses exclusively on the IUPAC, International Union of Pure and Applied Chemistry, system of nomenclature. In another video, we will talk about some of the common names of aldehydes, which you should be aware of. When naming aldehydes and other functional groups, we will assume here that you have a basic understanding of IUPAC nomenclature system. If you are unfamiliar with the IUPAC system, take a look at video number 310 from this library for more information on how to go about naming molecules in general. We will assume here that you have that groundwork already in place and are ready to dive in to the IUPAC system of naming aldehydes. So IUPAC naming of aldehydes. We're going to take a look at the rules for naming aldehydes, particularly how we differ in naming aldehydes relative to naming hydrocarbons and alkenes, which we talked about in earlier segments. When we are naming aldehydes, we are going to name the longest carbon chain that includes the aldehyde group. So we're going to name the longest carbon chain with the aldehyde group. This should seem very familiar because one of the key techniques that we've learned about in earlier segments was to name molecules you find the longest carbon chain. Here, in finding the longest carbon chain, that longest carbon chain has to include the carbon of the aldehyde group. Moreover, you are going to start numbering the chain at the aldehyde carbon. So number beginning at the aldehyde carbon. And then follow the longest pathway through the molecule. Once you reach the end of the molecule, the name of the parent chain, that is the last part of the name, is going to follow the template of taking the corresponding alkane names, such as methane, ethane, propane, butane, etc., dropping the E from that alkane name and replacing it with the letters Al for aldehyde. So drop the E from the alkane name that designates how many carbon atoms are in the chain, such as pentane, and append onto the end of it Al. So pentane, if it had an aldehyde group at one end, would become pentanal. There is no need to specify the numerical location of the aldehyde group. It will always be at carbon number 1. So no need to indicate the carbon number with the aldehyde group, because that will always be carbon number 1. We start numbering the chain, in other words, from the aldehyde group. So when we find that longest carbon chain, we decide to number it. Once we've identified the parent name, we're going to number with the aldehyde carbon as carbon number 1. So let's go ahead and try our hand at determining the name of some example problems. I'll go ahead and draw one out for us. Okay, let's take a look at this molecule. We're going to start by naming and numbering the longest carbon chain that has the aldehyde group. We'll start at the end of the aldehyde. So we'll start at this carbon right here, making our way through the longest pathway. We may be tempted to come this way, just following the zigzag pattern here, but that's not the longest pathway through the molecule. Instead, the longest pathway comes this way, down through here, because coming this way would give us only 3 more carbons, 1, 2, 3 in our longest carbon chain. Coming this way would give us 1, 2, 3, 4, following that longest carbon chain. So let's go ahead and take that path all the way through here to the end. Now we go ahead and go back in, number that longest carbon chain beginning from the carbonyl group of the aldehyde. We'll always begin at the carbonyl group of the aldehyde when we have an aldehyde group present. Numbering through gives us 6 carbons in our longest carbon chain, and therefore the parent name of this molecule is hexanal, because we took the E off of hexane and we replaced it with Al to indicate it's an aldehyde. Now don't be tempted to put 1 hexanal in here. That is absolutely not needed because it is implied that the aldehyde group absolutely has to be at carbon number 1 of that longest carbon chain. So hexanal, as the parent name, would incorporate all the atoms that we'd highlighted in yellow. It would also incorporate the carbonyl group and the hydrogen atom over here as well. Now our next task is much like before when we've learned about IUPAC nomenclature, is we need to name and number the alkyl branches. So I'm going to add that to our list of things to do here. Name and number the branches that come off of that parent chain. The parent chain is what we've highlighted in yellow. Everything that we haven't highlighted yet, we need to go back in and identify. So we have this group here, boom, and we have this group here coming off at carbon number 3. So let's go ahead and identify those, and we'll list those in alphabetical order as the prefixes that come before hexanal. At position number 2, back in video 310 when we learned about alkyl branches, we learned that this 4-carbon branch, 1, 2, 3, and the 4th atom is this methyl group coming off here, is referred to as an isobutyl group. So we could refer to this as an isobutyl group, put the number 2 there, dash in front of it, to indicate that it comes off of the parent at carbon number 2. And it's going to be an isobutyl because it's at that next to the last carbon atom of the straight chain where we see a methyl branch come off. That methyl branch of the next to the last carbon of the chain causes that to be referred to as an iso group. Then, branching off at position 3, we have a methyl group, so we'd call this 3-methyl. List those in alphabetical order in the name of the molecule just before hexanal. So iso of isobutyl comes before methyl, M. So we're going to call this 2-isobutyl dash 3-methyl hexanal as the complete IUPAC name for this particular molecule. Let's do this again for another example problem. I'm going to zoom out here so that we still have this information handy. So let's take a look at the structure in the upper right-hand corner here and devise an IUPAC name for this molecule. We'll start by following the rules, which is name the longest carbon chain that has an aldehyde group. We can map that out here, and I will go ahead and highlight in blue our longest carbon chain that contains the aldehyde group. So we start with our aldehyde. We come to here at this intersection, we have a choice to make. We can either come down this way, or we can follow this path. In this case, our best route is going to be through here because this gives us 3 more carbons versus coming down here, we have only 1 and 2 extra carbons in our longest carbon chain. So we come through this way, following all the way through the molecule. That's going to give us our parent name. I'm going to go ahead and highlight the hydrogen and the carbonyl oxygen there of our aldehyde group since those are part of the parent name as well. Now to determine our parent name, we start numbering. Add the aldehyde carbon as number 1. We follow through to 2, 3, 4, and 5. So since this is a 5-carbon aldehyde, our parent name here would be pentanal. The al suffix is our clue that this is an aldehyde group. Again, don't put the number 1 in front of pentanal. It's implied that since it's an aldehyde, the group is always at carbon number 1. Now we go about naming our branches. In this molecule, we have a branch at carbon number 2 right here, and I should use a different color to highlight that. So I'll go ahead and use a pink here to highlight through that. So we have our isopropyl group there, which I will go ahead and scratch in as 2-isopropyl. We again refer to it as an iso group because when we come into this branch, the next to the last carbon of that branch, right here, has a methyl group coming off it. So that's why it's called an iso group. So isopropyl, propyl because that's 3 carbons in total. Now in this structure, we also have coming off at carbon number 2 an OH group. And in this case, unlike earlier examples when we were in the alcohols chapter and doing nomenclature, here the alcohol group isn't the parent name. The parent name now is the aldehyde group. Instead, the alcohol is a branch, and when alcohol groups are branches, we refer to them as hydroxy groups. So we'd refer to this as a 2-hydroxy group here. Now plug those in alphabetical order before the name pentanal. We have isopropyl and hydroxy. H comes before I in the alphabet, so our 2-hydroxy is going to take priority here in listing out in the name. So 2-hydroxy, 2-isopropyl, pentanal would be the complete IUPAC name for this molecule. And a key learning point here to keep in mind in the future is that the rule is that aldehyde groups, which we can abbreviate as CHO groups, are higher in priority than alcohol groups for determining the parent. So in other words, if you have a structure like the one up top, where we have both an aldehyde group and an alcohol group, the aldehyde group is going to be what dictates finding the longest carbon chain and what dictates the parent name here. And then the alcohol group becomes a branch off of that. There's a whole hierarchy for determining names of molecules, where previously we learned in an earlier unit that alcohol groups, when determining the parent name, were more important than alkyl branches. And so when we were naming molecules at alcohol groups, what we did was we started numbering from the end closer to the alcohol group. Now that we've incorporated aldehydes into our mix, we learned that aldehydes are more important than alcohols, alcohols are more important than alkyl groups, and so this is the hierarchy we use to determine who is actually the parent chain determinant in the structure. So here, since you have an alkyl group, an alcohol group, and an aldehyde group, the aldehyde group is the most important. And this is a rule that is completely broad here. It's not just for this particular example problem, but it's something to keep in mind in general when naming molecules of multiple different functional groups. And you may be wondering where halogens fall in the lineup, because that's a type of group we've talked about before. Halogens are ranked here with alkyl groups. So if you have a fluorine, a chlorine, a bromine, or an iodine, those are going to rank less important than alcohol groups or aldehydes in determining what the parent chain is of your molecule. In the last video, we saw that a variety of flavors and fragrances have aldehyde groups directly bonded to an aromatic ring. We can talk about the nomenclature of molecules that have an aromatic ring directly bonded to an aldehyde group. When we have an aromatic ring, remember that that's this 6-atom ring with alternating double bond and single bond. It's abbreviated by a circle inside this 6-membered ring. So we could also draw this out like so. 6-atom ring, because there's 6 bends to that line, all connecting back together to make a ring, with alternating double bond, single bond pattern connected to our CHO group, our aldehyde group, would be referred to with the parent name of benzaldehyde. So if you see a molecule that has a structure like we're looking at up top here, and it has some extra branches coming off of it, recognize that the parent name, the last part of the name for that molecule, should be what I've written here, benzaldehyde. For example, if we had the following structure, we have our aromatic ring directly connected to an aldehyde group, which is sometimes abbreviated as CHO group. So don't let that throw you off the trail. If you see a CHO group, recognize that that refers to a carbonyl directly bonded to a hydrogen. And in that molecule, we had a second branch coming off right here. We would refer to this structure with the parent name benzaldehyde, where the benzaldehyde part of the name will refer to the aromatic ring, plus the CHO aldehyde group confers the parent benzaldehyde on that molecule. And then what we would do to name the remaining group there, where we have a hydroxy group, an alcohol group coming off of that ring, is we start numbering the ring with position 1 referring to the aldehyde group, take the shortest distance around, and that would put our alcohol group at position 3. We refer to an alcohol group as a hydroxy group, as we saw a few minutes ago. So this would be 3-hydroxy benzaldehyde. Now there is also a system of nomenclature referred to as ortho, meta, and para. And to review that, what ortho, meta, and para refers to is the relative positions of 2 different groups on an aromatic ring, which I will call Y and Z. There are 3 possible ways that those atoms could be arranged around the ring relative to one another. And I'm going to draw out those 3 as a reminder for what we can refer to these relative positions as. So we have our 3 possible options. These are the only 3 configurations that we can observe when we have 2 different branches bonded to the ring. Any other way that we could draw this would end up duplicating one of the ways that we've already drawn. And we refer to that pattern of branching as ortho, meta, or para, where if the two branches here and here on adjacent carbon atoms, we refer to them as being ortho to one another. You could also abbreviate that as O for ortho. If the two branches are separated by an undecorated carbon atom here in between, that is a carbon atom that has no branches coming off, we would refer to that as being meta or M. And then finally, if the two branches are at the 12 o'clock and 6 o'clock position, or in other words, directly across the ring from one another, we refer to that as being para. So instead of calling this 3-hydroxybenzaldehyde, we could also refer to this instead of 3-hydroxybenzaldehyde. We could match it with one of the patterns over here, and we could refer to as meta or M-hydroxybenzaldehyde because the two branches coming off leave a space in between there, one carbon atom of the ring that doesn't have a branch coming off of it. So I could synonymously write this out as M or meta hydroxybenzaldehyde. And that is going to tell us that the relative position of the two groups on that ring have to follow the meta pattern that we see up here. This only works if you have two branches coming off of an aromatic ring. It's only applicable to aromatic rings, and it's only applicable toward exactly two branches in total coming off of that aromatic ring. So you should be familiar with and able to name aromatic aldehydes that have up to two branches coming off of them, keeping in mind that the parent name for that will be benzaldehyde, and then whatever else is coming off will be named according to the jargon that we've previously learned for naming branches. In the next video, we'll continue to apply our learning of IUPAC nomenclature and use it toward naming ketone molecules.